So let's begin with this example question. So we're having this kind of situation. So two identical blocks of mass m each, balanced on a spring which is joined to both of them. So the spring is connected rigidly to both the blocks. So A and B are of mass, let's say 5 kilograms each, connected by a spring of spring constant 25 newtons per centimeter. Take G as 10 meters per second square. Now initially the system is in equilibrium. Now the block A is pushed down further by a distance of 6 centimeters and released from rest. So first of all, will the block B lose contact with the ground? And if so, then find its speed at the instant, find A's speed, not its speed. Find A's speed at the instant when B loses contact with the ground. Okay, Snigita, I have received your doubts from exercise number 2. We will discuss these questions today itself. To start with this question, we will discuss about the method. Just think about this closely. Okay. The hint is that again you can apply conservation of mechanical energy if you take the system inclusive of all the conservative forces. Okay. And you have to pay attention to what is the condition for B to lose contact with the ground. So the condition for that is normal reaction force on B should become 0. Okay. So ultimately, anytime you have a situation where something is losing contact with some surface or something, you have to make the free body diagram to understand that under what circumstances the contact force is becoming 0 or normal reaction is becoming 0. Okay, so to get the condition for which B will lose the contact, remember the idea is that the normal reaction contact force with the ground should become 0. So you'll have to understand the free body diagram situation for that to happen. Okay, so solve the equations carefully. Okay, I would like most of you to get the question correct yourself. Okay, Aman, I've received your doubts also. We will discuss those questions also. Okay, so I'm starting with the basic part of this question. So you'll understand that before you press the block A downwards, it was in equilibrium. So for equilibrium condition, for equilibrium, suppose this is compressed by x naught, then kx naught has to balance mg. Okay. And on this, of course, there will be mg, kx naught, and normal reaction. So x naught should be mg by k. So I believe that should be 2 centimeters. This is for equilibrium. Okay. Now from equilibrium, you're pushing it down further by a displacement of, okay, it's downwards further by a displacement of 6 centimeters. Okay. So that is basically 3 mg by k. So what will happen is that x1 will be equal to equilibrium condition plus the displacement. So it will be a total of 8 centimeters. So that is where you are starting from, or 4 mg by k. So this is your starting point for the system. After you push that block down, so you must have been applying a downward force on this to keep this compressed by x1, where x1 is so much. So this is at rest, this is at rest. Okay. Now you release the block A. Now the external force is released. Okay. So immediately as a result of that, A starts with a huge upward amount of acceleration. Starts with an acceleration because the spring force on it is way more than its weight. It's 4 times mg, the spring force. Okay. Whereas this will have a huge amount of normal reaction acting on it, because again the spring force is way more than its weight. Okay. So this is the starting position when you just release the block E. Okay. Now you don't need to calculate the acceleration because we are not going to be using dynamics for this part. Now see what happens, that from this position, as A starts going up, suppose we reach a condition where the spring becomes extended. Abhi kya ho raha hai? The spring is compressed by x1. But suppose the spring reaches a condition where it gets extended, then what will happen? The normal reaction acting on B will become less than its weight. Okay. So from this condition, if we reach a situation where something like this is happening now, A is somewhere here, okay, but now what has happened is that the spring has become extended by x. Suppose we reach this kind of situation. At this point of time, the spring force will become like this. It will become an inward force. So the normal reaction on B will become less than its weight. Okay. So if you now compare the displacement of A between this position and this position, if A is gone up by a height of h, that h should be equal to x1 plus x. So it's gone from compression of x1 to a extension of x. So in this situation, if you look at the FBD of B, it will show you that kx plus normal reaction is mg. So normal reaction is less than the weight by kx. So this will show you the condition for B to lose contact. For B to lose contact is that n is going to be 0. So kx should be equal to mg. So you should reach an extension of mg by k, or an extension of 2 centimeters. Okay, and obviously to reach that extension of 2 centimeters, A should be going up at that point of time. A should not have stopped, or even if it just about stops, it's fine. Okay, so basically the system should have enough elastic potential energy so that A can gain this much gravitational potential energy. Okay, so basically that is a condition now. So for the system to reach this state, that is extension of x equal to mg by k, or 2 centimeters, A should have v greater than equal to 0 at a vertical displacement of x1 plus x, or 5 mg by k, okay, or 10 centimeters. Basically what we want is that A should not have stopped, for h less than x1 plus 2 centimeters, or 10 centimeters. Okay, this is the condition that we're looking for now. So basically we have to investigate that by using work energy. But you can basically see that, it's always going to be symmetrical with respect to the mean position. So you started at 6 centimeters below the mean position. So A is not going to stop at a position of an extension of this much mg by k, because that is only 4 centimeters above the equilibrium position, and you started from 6 centimeters below the equilibrium position. So that symmetry itself is telling you that your A is going to reach this critical point where B tends to lose contact with the ground. So for example, if B was stuck to the ground, then in this case A would oscillate with an amplitude of 3 mg by k, or 6 centimeters, with respect to the equilibrium position. So it would have gone beyond, it would have gone above this point where B is losing contact with the ground. So once you gain that experience, you won't have to do this calculation. You'll understand that yes, B is going to be greater than 0 at this stage. Now the only thing we have to do is use work energy to find the value of B. So for that, just use conservation of energy between the first diagram and the second diagram. Use the conservation of energy between this diagram and this diagram. Okay, and you'll understand that that happens. 5 mg by k partner beta. So see what is happening. X1 kitna hai? 4 mg by k hai. Right? X1 is the initial compression, na? Right? And from there it is going to an extension of x equal to mg by k, because the condition for B to lose contact is that the extension x should be mg by k. So from a compression of 4 mg by k to an extension of mg by k, what is the total displacement h? H is equal to x1 plus x, no? So x1 कितना है मेरा 4 mg by k, और x कितना होना चाहिए mg by k, so that B loses contact. Okay, so this h, no, it is x1 plus x. Now for here we know that x1 is 4 mg by k. This we already know, which is 8 centimeters. But now we're also finding out that for B to lose contact, we want that x should become equal to 2 centimeters. So when x becomes 2 centimeters, h should become how much? It should become 8 plus 2, or 10 centimeters, or that is 5 mg by k. And that is the condition. So now that you understood this, I hope all of you understood this, you have to do the second part where you have to calculate A's speed at the instant when B loses contact with the ground. The symmetry is showing you that yes, B is going to lose contact with the ground because you've given it too much of a compression initially. Now you pushed it by 6 centimeters below equilibrium. So at a position where it's 4 centimeters above equilibrium, A is not going to stop before that. In fact, A is going to have a tendency to go further up. Okay, so apply conservation of energy between this state and this state. So take E plus B plus the spring plus gravitational field of the earth as your system. So change in kinetic energy plus change in gravitational potential energy plus change in springs potential energy should be zero. So A's kinetic energy is increasing from 0 to half mv square. So plus half mv square is your change in kinetic energy. A is rising through a height of h. So plus mgh is your change of potential energy. And the spring is going to a state of half kx square from a state of half kx1 square. So that is your change in potential energy. This should be zero, where x1 was a compression of 4 mg by k or 8 centimeters, and x is the extension. So this will give you v as a function of x, and of course h is equal to x1 plus x. We have that. So substituting all this, we are getting this, that half mv square is equal to half k x1 square minus x square minus mg x1 plus x. So we're getting the kinetic energy. Again, you'll notice that it's a quadratic function of x. Okay. So this whole part is a constant actually. And then we have minus half kx square minus mgx. So this is like this. The kinetic energy is like this sort of a function. This sort of function. Where alpha, beta, gamma are constants, you can see. So gamma x. This sort of a function. Okay. Anyhow, now what we want for B to lose contact, x should become mg by k. Okay. Or that is the same thing as 2 centimeters. Then at that instant, A's speed v is what we want to find out. Okay. So let's just substitute this. So half mv square should now become half k. I'm going to do this parametrically. You can do it by substituting the values also. But I'm doing it parametrically here. Or the easier way to do this parametrically is just to substitute in this. In this, I want to substitute just simplify things a little. Minus mg into 5 mg by k ऐसा term आ जाएगा. So okay, so ultimately we'll get 15 by 2. That's 7.5 minus 5. So half mv square will become 5 by 2 m square g square by k. So we'll get v as square root of 5 mg square by k, or g into square root of 5 m by k. This kind of term. Okay. So A speed at that instant will become 10 into square root of 5 into what was the mass of each block? I think 5 kgs, and the spring constant was 25 newtons per centimeter. So when we substitute it, it will be like this. So it will become interestingly 1 meter per second, if I'm not mistaken. I'm getting the speed as 1 meter per second for E. Now the fact that I'm getting the kinetic energy as a positive quantity, that's showing me that definitely yes, this situation is going to happen. Suppose the system was stopping before reaching this state where B is losing contact, then on solving this, I would have got this half mv square as a negative quantity. So that would have told me that no, he is not reaching that height of, of 10 centimeters from where it started, where B will lose contact. A is stopping somewhere before that. But in this case, that's not happening, as I've told you by the symmetry thing also. So just check my calculation and finish up this question. Anybody else got this answer? You can also do it by substituting the numerical values in my equations only. I've done the solving parametrically because I prefer it that way. But yeah, Aditya, I'll show the question. So these were the values in the question, statement of the question and the values of the question. Okay, so done now. So I'll come back to the solution now. Okay. So basically, I'll put this diagram here again so you can relate with it. So now you can see how this equation, the values I've substituted for each of the terms, correlates in this, going from 1 to 2. This is conservation of mechanical energy. And here I have written the equation for diagram 1 to diagram 2. Okay, so hope all of you are getting this question. If anybody has a doubt in the solving part, please let me know. Okay, very good. So now I'm going to move to couple of the doubts. Okay, so I'm going to intermix my questions which I'm giving you to solve with solving of your doubts. Okay. So a couple of questions we'll solve from the exercise, then we'll come back to some questions I want to discuss. That way we'll keep doing both the things. Okay. So Nikita, I think question number 5 of level 1 exercise 2. This is the question you asked, better. Okay. So see in this, what is happening? The kinetic energy of the body is increased by 300%. Okay. So what does this statement mean? This statement means that the final kinetic energy is the initial kinetic energy plus a certain increase. No? So that increase in kinetic energy is 300% of initial kinetic energy. This is the meaning of this statement. So that means, so this statement means that the final kinetic energy is how much? It is 4 times the initial kinetic energy, because the change only will be 3 times. Understood this now, no? So from that you can see that v square is equal to 4 times u square. So that means v is equal to 2 times u. The final speed is double. Okay. So the momentum will increase by how much? Okay. Now see, this is a very, in that sense, it's a very tricky question. It should say the magnitude of momentum has changed by how much, because exactly the momentum has changed by how much we can't say, because it's a vector quantity, no, momentum. So when they say momentum, you have to interpret this as magnitude of momentum. Mod of momentum has changed by how much? I mean, it is like delta of uh, mod of p. That is how much. So that you can see is going to be 100% change, because momentum's magnitude has changed by 100%, has increased to double. No? But why I'm saying that this is a statement on its own which is wrong, because you could always have a situation like this where your initial momentum was like this. You know, it was in this direction and it was some mu. And let's say after some time, your final momentum is in this direction. Okay. mv, that is 2 times mu, but it's in this direction. So now if I look at the vector quantity of change in momentum, delta p, then in this case that delta p is p final minus p initial, but as a vector it will become, so magnitude of delta p now will become how much? It will become the sum of these two, so it will actually become 4 mu. Okay, but if I say, yeah, what is the change in the magnitude of momentum? Okay, then it's okay, then it's regardless of the direction of momentum. It is, so if I talk about this change in magnitude of momentum, so that is equal to what? Magnitude of final momentum minus magnitude of initial momentum. So that has to be irrespective of direction. It has to be mv minus mu. So it has to be m into 2v minus m into u. So it has to be mu. So that is 100%. So just make a correction in the language of the question actually. Now this should be the its momentum's magnitude will change by how much? Its momentum's magnitude changes by, okay, because you can get a more interesting question at JE advanced level, where one option is saying that no, we cannot actually say how much the momentum's magnitude is, sorry, how much the momentum is changing by, because actually we cannot say, because we don't know the angle by which it's turned. So all of you are understanding this point. Nikita, is the question clear, beta? Okay. Let's move on to the next one from exercise 2. Okay. So I am receiving so far doubts from exercise 2, some of them, and then some doubts from exercise exercise 5 after this. Okay, so I'm clearing the doubts of exercise 2 first. So Jenny, you have asked question number 9, and then couple of people separately have asked question number 13. Okay, so I'm going to question number 9, then I'll come to 13. Okay, so just go through the question and I will explain this on my whiteboard because I'll need some space. So chain is held on a frictionless table with 1/3 of it hanging over the edge. So this is the initial state of the chain, let's say. L by 3 part is hanging over here, and therefore 2L by 3 is on the surface on a frictionless table. Now you want to pull it so that what happens, the entire chain comes on the table. Okay, so how we'll calculate the work done, how much work the external agent has to do to pull the whole chain back on the table. Okay, so let's understand how this will come about. So I'm switching to my board. So you can do like this, that my initial state now, the chain was like this. Okay, so if I take this as my reference level, okay, so this is my origin point. Okay, so 2/3 of the length is at y equal to 0, and 1/3 of the length is at like this. Okay, at vertically hanging. So this 1/3 part, its mass is going to be how much? Its mass is going to be m by 3, and its center of mass is going to be at what position? Its center of mass is going to be at y equal to minus L by 6 because it will be at the midpoint. Okay. Whereas this part, its mass is going to be 2m by 3, and its center of mass is over here. So its center of mass is at y equal to 0. Okay. So I can write the initial potential energy, the gravitational potential energy, as some reference level potential energy minus m by 3, that is the mass of this part, into g into L by 6. We'll write the energy basically as U naught plus m1 g y1 plus m2 g y2, like this. So this term is 0 and this term is so much. So it is some reference value minus how much? mg L by 18. This is the initial potential energy. Now on application of this force and all that, when you pull the chain completely on the table, now its entire mass is on the table, and I've taken the table's level as my y equal to 0 coordinate. So understood now immediately now what's happening. So the entire mass, its center of mass is on the table, so its y coordinate is 0. So the final potential energy is becoming the reference level plus 0. Okay. So, and there's no kinetic energy involved. Here also the final speed is 0. Here also the initial speed was 0. So work done by my external agent will be equal to change in the gravitational potential energy. So that is final minus initial. So you can see that is plus mgl by 18. So here we have made use of the center of mass concept. Okay? That if a body's center of mass is at some y coordinate yc, okay, with respect to the origin of our coordinate system, then we can write the gravitational potential energy as the reference level potential energy plus mg y of the center of mass. Okay. Now, since you are doing center of mass, it's actually very easy to prove this formula. You can just take a mass dm, which is at a y coordinate y. Okay, so if you take any mass dm, its potential energy becomes how much? It becomes dm gy. So the total potential energy becomes integration of dm gy. So that is integration of y dm. Okay, so that is nothing but y coordinate of center of mass into total mass. So that's how we get this. That's the concept of center of mass, that in a uniform gravitational field, you can replace that entire distribution of mass of the chain or of any body like this with an equivalent particle at its center of mass, and it will have the same effect as far as gravity is concerned because we are in a uniform gravitational field. Okay, so I think this question was from Jenny Beta. Hope this is clear for you. Yes, Jenny, the question is clear. Okay, very good. Now let's move on to 13th question. So I'm switching back to the exercise. Question 13 has been asked by multiple people, so I'll discuss it. Okay. Yeah, this question has a language which one has to interpret carefully. Okay. It says that it requires 20 turns of the stem of a watch. So I'm assuming some of you have seen these mechanical watches, where you have to turn the stem of the watch in order to, uh, you know, wind the watch, so called. We used to say that wind the watch so that it has mechanical energy. So when you turn the stem of the watch, what is happening is, by the angle by which you're turning, proportional to that, you are basically compressing a spring. Okay. And by compressing the spring, you're storing sufficient potential energy in it for it to keep the watch running for a certain duration of time. Because basically what happens is, as the hands of the watch are moving, uh, they are having to, they are having to overcome the drag forces, like the friction at the axle, the air resistance, and these kind of forces. So the system loses mechanical energy. So that's why if there's no source of energy to compensate for this dissipation of energy by the drag forces, then the clock will start to lose time. So in modern day clocks, in electronic clocks, that is provided by an electrical source. Or you might have heard of very advanced mechanical watches like Seiko kinetic watches made in Switzerland, where you don't need to wind the watch, because what the watch does is, from the movement of your hand, the amount of mechanical energy that the watch gains from the kinetic energy because of the movement of your hand, it automatically, a mechanical system stores that kinetic energy as potential energy. So as long as you're wearing the watch in your hand and you're not keeping your hand stationary forever, you will gain enough energy. You will be uh, developing enough energy through the motion of your hand for the watch to be able to compensate. So those are very advanced modern day watches. But the type of watch this one is talking about is an old style mechanical watch, where you need to wind the watch. So you have a small pin kind of thing attached to a cylindrical kind of thing, and you need to keep winding it once every 2 days or once every 3 days. Otherwise, you'll notice that the clock starts to lose time. Or if you've seen those grandfather clocks also, the grandfather clock typically has a key. You have to insert the key and you have to rotate that key to wind it. So if you have one at home, then probably one of your parents will be after you every day. That it's your job to wind it once every day, so that the family doesn't lose time. That used to happen in my childhood. We used to have a grandfather clock near the dining table. It was my job after a time to wind it every day. So anyway, so when you wind that watch, or that clock or whatever, you're storing potential energy in a system of springs inside. So now the thing is, the angle by which you wind the key, okay, or the stem, what they're calling the stem over here, that is proportional to the extension of the spring or the compression of the spring. Okay. So when you wind this, when you're winding the stem or turning the stem through an angle delta theta, that is proportional to the compression x given to the spring. And the potential energy stored in the spring is proportional to x square. Okay. So that means, now see what is happening here. In the initial thing, they are saying that uh, you are making 20 turns. Okay. So the angle rotated for 20 turns is 20 into 2 pi. Okay. So that is proportional to some x1, let's say. Okay. And that x1 is sufficient for, in terms of energy, to keep it running for 30 hours. Okay. So x1 square is proportional to 20 hours. Okay. So that means 20 turns into 2 pi whole square is equal to some constant of proportionality, let's say c, into, sorry, 30 hours, into 30 hours. Okay. So now the same thing, if you turn it by only 10 turns, okay, so 10 into 2 pi whole square will become proportional to some different amount of time. Okay. So just compare these two equations. If you divide them, you can see that 4 by 1 is equal to 30 hours divided by this unknown time delta t. So my delta t time should be what? 1/4 of 30 hours. So it should be 7.5 hours. Okay, so the answer should be this one. So hope this question is clear. Okay. So what we are saying is that the amount by which you rotate the stem of the clock, that is proportional to the compression given to the spring, and the potential energy stored in the spring is proportional to x square. No? So ultimately your angular displacement given to the stem, uska square is proportional to the energy stored, and that energy stored is proportional to the time for which the clock will run, because the clock utilizes a certain amount of energy per unit time. Okay, so just use this proportionality now. So your delta theta square is proportional to the amount of time for which the clock is running. So in one case it is 20 rounds, in the other case it is 10 rounds. So the delta theta is in ratio 2:1. So the total energy should be in the ratio 4:1. So the time should be in the ratio 4:1. So that's why in the second case, when you wind it by only 10 turns, okay, you are going to get 1/4 the amount of time for which the clock will run. Okay, so people, hope this is clear. So I think, okay, very good. Okay, so that was question number 13. Now I've also been asked question 23. So let's discuss that. So 23, now we are moving on to level 2. Okay, so let's look at this question. So it says that a car starts from rest, moves on a surface in which coefficient of friction between the road and the tires increases linearly with distance x. Okay, so this is giving you a hint that mu is a function of x. That means we'll probably have to do some kind of integration. The car moves with maximum possible acceleration. So the kinetic energy will be what kind of function of x? Okay, so I'm going to explain this on my board again. So I'm switching. Okay. So in this example, this is question number 23 from exercise 2 of the module. Okay, stop howling. What happened? Yeah, so in this, what is happening is that the maximum possible acceleration that a car can get actually interestingly depends on the coefficient of friction between the tires and the car, as we have discussed earlier, because friction is generated like this. So friction is equal to mass into acceleration. Okay. So maximum acceleration is maximum friction divided by mass of the car. So it is equal to mu g. Now this car is moving at maximum acceleration, so that will be equal to mu g. But mu is a linear function of x. So it is, let's say, mu naught by L into x, or some, I mean, we can just say it is some constant into x, but it is, let's say, alpha x, where alpha is some constant. Cooking. Oh, okay. Okay, so this is happening over here. Okay, so that means as the car is moving now from x equal to 0, it starts, let's say. So when it is at some x equal to x, the acceleration of the car, which is the maximum acceleration only, which is mu g, is equal to alpha xg. Okay, or your acceleration is proportional to displacement. So we have to find what? We have to find the relationship between the kinetic energy and x. So to find the relationship between kinetic energy and x, you just need to find v. V as some kind of function of x. So then kinetic energy will become proportional to that function square. So we need to find this. Okay. So now this is a kinematics thing. Now, when you know the relation between a and x, how to get the relation between v and x? Instead of expressing a as dv by dt, express it as v dv by dx. So this is one way of doing it. Okay, where I'm avoiding work energy, just doing this. Okay. So v dv by dx is equal to some constant alpha into xg. So v dv integration is going to be x dx integration. So v square is going to be proportional to x square. That means v is proportional to x. Okay. So kinetic energy is going to be proportional to x square. Now the work energy method will be also very similar to this. I'm coming to that. How is E max equal to mu g? No? Okay, so that's actually a very complex process, but I'll explain. So when a car accelerates, what happens, Nikita, is that through the engine, torque is transmitted to the wheels. Okay. Torque is transmitted because the engine cannot directly apply force on itself. So this torque causes the point of contact to have a tendency to slip backwards. So the ground applies a friction in the forward direction on the wheel. You understanding? And I'm saying that's the same for all the wheels if it's a four-wheel drive car. Okay. Okay. So on the whole body of the car, what is the net external force acting? It's friction. So that is equal to m into a. Now, depending on how much torque the engine can generate, more and more amount of friction will be required till the skidding starts. So this friction is a sort of static friction. It is actually called rolling friction. You're going to understand this very soon in the chapter of rotational mechanics, but it's a type of static friction because the wheel is not skidding. That's what we are assuming. So the maximum friction that is available is mu into normal reaction. So that is mu into mg. So that's why the maximum acceleration the car can have, where m is its total mass, is equal to mu g. The same thing we discussed in that H.C. Verma Superman problem. Remember Superman running on the ground. Okay. So if the coefficient of friction between his shoes and the ground is mu, then maximum acceleration is mu g possible. Okay. So now the other way we can do this is as the car is moving, okay, the friction acting on it, that is the net force, and that is equal to alpha into x into g. So alpha into x into mg. Because maximum friction is acting, so it's mu mg. So that is alpha into x into mg. So work done by friction now, and remember this is not kinetic friction. So that is going to be equal to the change in kinetic energy. But this is actually a wrong thing over here because the whole thing is actually more technical. The car has an engine and actually friction doesn't do work. So it's okay in this chapter you can approach it this way, but friction does not do work because it's a combination of rotation and translation. So I don't want to give you this method because it's technically wrong. The statement itself is not correct. Actually friction does zero work because the wheels are rolling. So actually what happens is that it is the energy lost by the engine. Okay, this is, you can say, the change in internal energy, okay, which will be negative because the engine consumes fuel. So it loses internal energy or chemical potential energy, and that gives its kinetic energy. So that's actually what happens. Similarly, when an athlete is running, or even when you are running, your foot is in contact with the ground. Okay. I'm not good at drawing and also. So when one of your feet are in contact with the ground, okay, now you're trying to push the foot backwards. Okay, you're trying to make it skid backwards. So the ground is applying the friction on your body, and that is giving you acceleration. But the work done by this friction is how much? Is zero because this is static friction. So if your kinetic energy is increasing, where does your increase in kinetic energy come from? It comes from the loss in your biological internal energy. You're burning calories to generate that energy, which is doing work on your muscles to alternately contract and expand your muscles, and with that action the muscles are able to generate friction. But the point of application of, so again that thing of work done is f dot ds, where ds is the point of displacement of point of application of the force. So because it is static friction, so if your feet don't skid, don't skid. Okay, then work done by friction will be zero, because the point of application of friction on your feet is at rest. It's not skidding, it's not having any displacement. Okay, so it is not friction that does work on your body to give you the kinetic energy as you are accelerating. It is your own internal biological energy which you are expending to alternately contract and expand the muscles, and that is giving you the kinetic energy. But acceleration is generated by friction, because friction is the external force. So friction is equal to mass into acceleration. But work done by friction is not there. That is zero. Work done by friction is not equal to the change in kinetic energy. It comes from the loss in biological internal energy. So anytime you have a biological entity, no, like an insect climbing a ladder or a person running or something, you cannot apply conservation of mechanical energy because there's biological energy also involved. So you have to be careful about this. Okay. Hope you people are understanding the point. Yeah, so Ayush, when you apply brakes, na, again, it depends on whether you have applied brakes enough to skid or not. So, you know what has happened is that before you applied the brakes, the engine has applied torque and given the wheel already some angular speed, and your car already has the linear speed. You learn all this in rotation very soon. But now when you apply the brakes, na, there is a tendency, so the brake is giving a tendency of the wheel to decelerate angularly. So now there's a tendency for the wheel to slip in the forward direction. So friction acts on it in the backward direction. So the deceleration to your car is again coming from friction. But as long as the wheel is not skidding, the work done by this friction will be zero. Okay. So the loss in kinetic energy is coming actually from the energy dissipated at the axle of the wheel, not by the friction on the ground. If it skids, it's a different matter. Then there is kinetic friction acting, and kinetic friction always dissipates energy. Okay. Yeah. So for this particular question, the working, we will use kinematics. We will not use, Nikita, I'm coming to it. We will not use work energy, because when there is a vehicle which has a combustion engine, or when there's a biological creature who has internal biological energy involved, we cannot apply conservation of mechanical energy, that kind of concept. Okay. So this question is there here probably to just explain that fact to you. So this this was the acceleration. Okay. So yeah, earlier in the working of the question, we understood that the acceleration was like this. It was alpha g, which is a constant, into x. So v dv by dx is equal to this constant alpha g into x. So we integrate this. V dv is alpha g into x dx. Integrate this, so you're getting v square is proportional to x square. Now v square is only proportional to kinetic energy, so your kinetic energy should be proportional to x square. No, so skidding is when there is slipping at the point of contact. Okay, skidding is when the friction acting between the point of contact on one body and the surface is kinetic friction. And no skidding is when there is either no friction or there is static friction, because there is no slipping. Slipping and skidding are one and the same thing, Ayush. Yeah, friction plays a role in the brake system, no? But that is not the friction with. So see, there are two frictions, no? One is, see, in the brake system, no, on the rim of your wheel, there is some kind of jamming which is happening. Okay, so whether it's a disc brake or it is a drum brake or whatever, no, something is jamming against the rim of your wheel, and that is generating kinetic friction over there, and that's dissipating energy. Like, in the modern day bikes, you see, in the front wheel there is disc brakes, so there are those nice looking metallic rims which have holes in it, you know? So that is for the braking system only. Okay, whereas there's another friction that acts between the ground and the rubber of the tire. So unless you jam the brake so much that the rubber of the tire is actually skidding against the ground, unless that is happening, the friction between the ground and the rubber of the tire is not going to be kinetic friction. It is going to be another type of static friction, which is called rolling friction. So you will learn this in the chapter of rotational mechanics in more detail. Now when you learn that in that chapter, you will see rolling friction does not do work, because like static friction, it acts at a point of contact which is at rest. So it's a very interesting thing actually. It's like all the things that you're learning in mechanics right now, you will put them all together. All those concepts will come together in that section of rolling within rotational mechanics, and you'll understand this better then. I think another few days and you'll be at that position to understand rolling, okay, because you are completing center of mass chapter now. Okay. So yeah, so these were the questions from exercise 2. Now next we'll move on to exercise 5, but before that I want you to solve some more questions. So again in the cycle, okay, I'll get back to this discussion. Let me give a question for everybody to solve first. Okay, so now I'm coming to the slightly more tricky type of questions as far as constraint relation is concerned. I told you that constraint relations are something which are important throughout mechanics. We started with constraint relations in the chapter of Newton's laws, but they will be significant in our mechanics problems throughout. Okay. So you have this smooth wall, I said 90 degrees to the smooth floor. Now you have this like dumbbell shaped object, which actually consists of two particle like spherical balls kind of things. Okay, so they are not very big, these ones. You can treat them like particles only, and they are connected by light but rigid rod. Okay. So two small spherical particle like balls, they are connected by a massless or light rigid rod like this, and you place this system, this dumbbell kind of system, against the wall at a certain angle and release it. Okay, so let's come to the question. So A and B are identical small spherical masses m each. Okay, connected by a massless, and as you know, nothing is perfectly massless, but by that we mean light. Okay, massless but rigid rod. Okay, so like if these are metallic spheres which are of high density metal, let's imagine the rod joining them is like very low density plastic, so its mass is negligible, so something like that. Okay, of length L. Okay, so the system is released from rest from a position where this angle is 53 degrees. So this system is released from rest with the rod at 53 degrees to the floor as shown. Okay. So now what will happen is after some time, this will come sliding down, that kind of situation. Okay. So this system will be sliding such that B will be sliding horizontally towards the right, and assuming that A doesn't lose contact with the wall, A will be moving downwards vertically. Okay. So now let's say that after some time what has happened is that this system of ours, this has come to a state where the rod is now making 37 degrees with the horizontal. So at that instant, what is the individual speed of A and B? We have to calculate that. Okay. So we have to calculate that by the time the system has become like this. This angle has become 37 degrees. So at this moment, the instantaneous velocities of A and B are like this and like this. So we want to find VA and VB at the instant when theta is equal to 37 degrees for the rod with respect to the flow. The angle has become 37 degrees. Okay. Now for doing this, it is given to us that the length of the rod is 20 meters and the acceleration due to gravity is 10 meters per second square. Okay. This is the information given and this is all the information that we need. We'll get VA and VB in meters per second. Okay. So just start with this and I shall come back to your question about the rotating wheel and all that. Okay. The bicycle question that you just asked me, I'll explain that also. Okay, so this is a very interesting question to demonstrate the application of calculus also. And of course, work energy application is there in it. So if we are taking some intermediate instant, when the position of the rod is at some intermediate angle theta, this angle is theta, and these speeds are VA and VB like this. Okay, Kevin, I'll verify your answer. Seems correct. Okay. Now, one easy way to understand this is that if you take the position of the sphere E with respect to this origin point as y coordinate, and the position of B with respect to the same origin in terms of an x coordinate, x, this is y. So you have a constraint relation that x square plus y square, which is equal to L square. Now L square is a constant. Okay, but x and y are changing such that in the diagram you can see dx by dt is equal to plus of VB, because x is increasing at the rate, whereas dy by dt is equal to minus of VA, because the instantaneous rate at which y is decreasing is equal to the downward velocity of the point. Okay. So now what you do is you differentiate this constraint relation, this do rate of change for this. Okay. So d by dt of x square plus y square should become 0, because rate of change of a constant should be 0. Okay. So you have a constraint relation between VA and VB now. So when you differentiate this, you'll use chain rule. Okay. So you use this principle that differentiation with respect to time of x square will become differentiation with respect to x of x square into dx by dt. So it will become 2x dx by dt. So like that, the second one also. So 2x into dx by dt plus 2y into dy by dt will be 0. So x into VB, okay, minus y into VA, because dy by dt was minus VA, should be 0. So VA should be equal to x by y times VB, okay, or that is equal to VB cot theta. So this is my constraint relation. Okay. Okay, I'll just check it out. Okay. Okay. So this is my constraint relation. So now at theta equal to 37 degrees, VA will be VB cot 37. So cot 37 is the same as tan 53. So 4 by 3 VB is the first thing. Okay. And then use conservation of energy. Okay. So I'll come to that. Just write this down. Okay, so now when you compare from the initial state, now normal reaction is not doing any work. Gravity is an internal conservative force. Okay, so half mva square plus half mvb square minus mgh for A should be 0. So going from that 53-degree position to this 37-degree position, okay, this one is having a vertical displacement in the downward direction of HA. So that HA will be equal to how much? It will be L sine 53 minus L sine 37. So it will be L by 5. So the particle A sliding down the wall, it doesn't matter na beta, because delta U nikal rahe na. So delta U is mg delta y na. We're not expressing the absolute potential energy now. I'm just calculating change in potential energy. So I don't need any reference for that, for gravitational potential energy. So that's why I have not taken any reference level here. If I were writing the initial value of potential energy and the final value of potential energy, then I would need to define the origin of my y coordinate as a reference point. But here I don't need to do that. Nee, so delta y is negative, na beta. That's why delta u is negative. The particle is coming down na, vertically. So that's how I know that my gravitational potential energy is decreasing. So my delta y for E is minus HA, no? And my delta y for B is 0, because this is so that's why my delta U for the system is just minus mg HA. Okay, so I've got this now, that half m VA square plus VB square is becoming mg into, so my second equation, and I've just seen that this is L by 5. L by 5. So I have VA square plus VB square is equal to 2 by 5 GL. Now I'll substitute this here. So VA square, or rather VB square, okay, into 16 by 9 plus 1 is equal to 2 by 5 GL. Okay. Now I can just use the value of L I've given, which was 20 meters, and G as 10 meters per second square, and verify the answer. So 25 by 9 VB square is equal to 2 by 5 into 10 into 20. So VB will become square root of 9 by 25 into 2 into 2 into 20. Okay. So that is 3 by 5 into 2 into 2 into root 5. This is what I'm getting. So I'm getting VB as 12 by 5 root 5 meters per second. And accordingly, VA should be 4 by 3 times this. So that will become 16 by 5 root 5 meters per second. You can just verify my calculation, but this is the method you have to use here. Okay. So I'm taking you through the constraint relation concept again, and then we look at the application of work energy theorem of conservation of mechanical energy. Okay. So Kevin, your answer is matching now. Wait, I'll just numerically verify it. Okay. Okay, good. Okay. Now let's move on to some more questions from exercise 5 now. So turn to exercise 5. There are a few doubts which have been asked, so I'll discuss them. Okay, so we will start with question 36. So that's the subjective exercise number 5. Wait a minute, I will just put this up. Screen share. Yeah. Okay, so question number 36. Let's go through it. So basically what we have to do here is conservation of mechanical energy. So what we can do is you can take this as your reference level. So in the initial picture, you can see that the initial potential energy will be some reference level potential energy plus 0 for the first particle, okay, and minus mg into this vertical height. Now this vertical height for this one will be how much? It will be r sine 45, so r by root 2. Okay, so this is your initial potential energy, and by the time your system is coming here, okay, your final potential energy is becoming the reference level value minus mgr minus mgr. Both of them are at a vertical coordinate which is minus r compared to my origin. Understood now? So from this you will get your change in potential energy of the system. Delta U is becoming how much? Final minus initial. So there's a loss of potential energy. You can see it is mgr. If you take common, there is minus 2 plus 1 by root 2. Okay, I'm just doing this directly, but you can see that if you subtract this minus this, you'll get this. So Naman, is this clear, beta? Okay. So that is equal to your kinetic energy. Okay. So your system started from rest over here. So this loss in potential energy will be equal to the gain in kinetic energy. You have a common speed of v. Okay. So delta ke plus delta u is 0. So 2 times half mv square. Okay. And I'll take this delta u to the other side. So it will become mgr into 2 minus 1 by root 2. इसका negative हो जाएगा. Okay. So from this you calculate v. And once you got v, now you make the free body diagram for the first particle. So that first particle is still in circular path. It's not yet come to the straight path. So on it, normal reaction and mg should act in such a way that it has a centripetal acceleration of v square by r in the upward direction. So the free body diagram will tell you this, that for this particle 1, n minus mg should be equal to mv square by r. So now you substitute that v from here, you will get the answer. Okay, hope this is clear, Naman. You can complete the calculation now. Okay. For calculation, you can use the shortcut that 1 by root 2 is root 2 by 2, which is approximately 0.7. Okay, now next we'll go backwards to question number 18, which Aman has asked. Okay, so I'm clearing this and I'm going back to question 18 of the same exercise. Yeah. Now this is a very interesting question, and just go through the question. I'll explain this on my whiteboard. So remember that here the force that you are applying, that force is a constant force. This force here, okay, is a constant. It's a vertical force of constant magnitude. Okay. And we have to find the speed of these two by the time theta approaches 90. Okay. All right, so I'm switching my screen. So I'll explain this like this now. Okay. So exercise 5, question number 18 it is. Okay. So what is happening is, I'll assume that we started our system from this position here. Okay. This is when we started applying the force, which is constant at this point. Now I will just take this value instead of theta, I'll take it as theta naught because it's the initial value. Okay. So speed was 0 for both of them. This is where the system started from. Now after some time, what is happening is that the system is progressing to this state now, that your two spheres have come closer to each other because you're pulling with that force from above. The point of application of the force is therefore gone up and theta is therefore increased. So though we want to ultimately solve for theta tending to 90, but I'll just first write it for some intermediate theta. So now this is increased to some theta from theta naught. So the point of application of the force is here. Okay. And by now these two have gained some speed v. So it being a frictionless surface, what is happening is that the work done by that external force is equal to the change in kinetic energy of the system, because the internal force of tension will not be doing work. The tension will act in such a way that the work done by tension will be 0 for the system. Okay. So if you take the rope plus the spheres as your system, then work done by F is equal to change in kinetic energy. So work done by F अभी कितना होगा? ये वाला जो height है, H1 suppose, H1 is L cos theta naught, sorry, L sin theta naught. Okay. And now this height is become H2 here. So H2 is L sin theta. So the change in, so the work done is going to be F into the vertical displacement of that point P. The vertical displacement of the point P. So that is going to be F into L sin theta minus sin theta naught. Okay. This is going to be the work done by F. Okay, that's this. And that should be equal to the change in kinetic energy. So that is 2 times half mv square. So there you are. It's very easy now. So you have FL sine whatever value finally minus sine theta naught is equal to mv square. This is your formula finally. Now when they are going to collide, your theta is tending to 90. So just put sine theta as 1. Okay. So when the spheres are about to collide, the theta is about to be 90 degrees. So FL into 1 minus sine theta naught, that should be equal to mv square. That is the speed of collision, right? That is the final speed. Okay, Aman, so hope the question is clear, beta. Okay, good. So I'll switch to another question now. So this is again exercise 5, question number 39. Let's discuss this. So just go through the question, I'll explain. So you have this smooth semicircular thing, okay, tube. It's smooth from the inside. Now it has a heavy, flexible, uniform chain which is just about fitting inside it. So the length of the chain is pi r, as you can see. Now, assuming that you give it a slight disturbance so that the chain starts to move, find the velocity when it will emerge out of the point B. So the chain will just come to this kind of vertical position when it slips out like this and then just comes here, such that the chain is just like this. So at that moment, we have to find the velocity. So this is again something in which we can use the center of mass formula, because you already have probably done the derivation of center of mass of semicircular arc, being at a distance of 2r by pi from the center of curvature. Or we can do integration to find the potential energy if we are not aware of the position of the center of mass. Either way we can do it. Okay. Okay. So what I will tend to do here is I tend to show you by the integration method, and then also later show that the formula works. Right. So I'll take the initial position of my chain. I don't need to show the whole other things and all that. Okay. So I'm not drawing the tube and all that because the tube doesn't play a role as far as energy is concerned. The contact force between the tube and the chain does not do any work. So this is the initial state of the chain. And I'll take the center of curvature as my origin. So with respect to my origin, I can write the potential energy as U naught plus integration dmgy, where as usual, I'll take an angular position theta for a differential mass dm, and its y coordinate will become r sine theta. So y will be r sine theta, dm will be m upon pi r into r d theta. Okay, so that's standard kind of integration. But now we are doing for potential energy instead of this. So this will become m upon pi into r sine theta d theta. Okay, and we are integrating from here to here. So e to b. So A के लिए we'll take theta as 0, B के लिए we take theta as pi. Okay. So this will become, so G also mgr by pi cos theta from 0 to pi. Okay, so you can see this is nothing but the y coordinate of the center of mass with respect to the origin node. You know that this system center of mass is here. So the y coordinate of the center of mass is 2r by pi. You've done that by integration. So you can also express the initial potential energy as u naught plus mg into y coordinate of the center of mass. That's the same as this. Okay. That's very easy. And now by the time the chain comes to the second position where it's like this, it's over here. So by the time it comes to this position now, this was all part of the initial actually. So I'll just label this as the initial potential energy. Okay. Now in this second state, it's like this, and the length of the chain is pi r, and its center of mass is here. So here I don't need to do integration once more. I can just see. Okay. So in the final state, potential energy is u naught minus mg into pi r by 2, because the y coordinate of the center of mass will be minus L by 2 in the final state with respect to this origin. Okay. So there you are now. So your half mv square plus delta u should be 0. So half mv square should be equal to this. Okay. So in many ways, this is like an application of center of mass along with work energy theorem. This kind of problem. So hope this is clear, Naman. Okay. Okay, now there's one more question that I want to discuss, which is part of a question from your module also, but not directly, indirectly. So you would have seen this is part of a question somewhere in exercise 2, I think. So what is happening is, in my question, there is a hemispherical surface inside which there is a particle which is initially at this position, let's say at the position A. Now it's being dragged from this position to this position B, where it goes from the lowest position to an angular position of something, let's say 30 degrees with respect to it. But while it is moving now, there is a external force that acts on it, such that that external force is constant in magnitude, but always pointing towards this point here, this corner point here. It's always pointing towards that point. It's constant in magnitude and is pointing towards So an external force of constant magnitude okay, acts such that its direction always points to this particular point over here, which is C. Okay. So find the work done by this force from A to B. Okay. So take down this question and I'll start explaining it, okay, because it will take a bit of time to go through this question. So I want to finish this today. So there are 2 or 3 different ways by which we can do this question. And one of them is a trick which will make it very, very easy. Okay. But the other 2 ways will involve a bit of integration concept. Okay. So the first method is that we can just use the integration f dot ds concept to calculate the work done. But this is going to make quite a difficult situation. I mean, difficult in the sense that it will be lengthy, nothing else. Okay. So when that particle is at a general position like this, and it's at a general point like this, okay, where this angle is theta. Okay. So when it's at a point like this, then what is happening is that my force vector is pointing along this chord. My force vector is pointing along this chord. Whereas my differential displacement vector, that is going to be tangential to the circle at that point. So my differential displacement vector, that's going to be like this along this. And if the radius of the circle is r, so the chord EC. So we have to basically now, so I know that ds magnitude will be r d theta, okay, because this, okay. But I have to now find this angle, and let's say I'm calling this angle something else because theta I've used as the angular position. So let's say I'm calling it beta. So for that small displacement f dot ds, this will become f ds cos beta. So this will become f into r d theta into cos of beta. Now beta I will have to relate with theta. So how I'll relate beta with theta is like this, that notice this triangle, it's a isosceles triangle. Okay. So this angle here is equal to this angle. Okay. So let's call this angle phi. So in triangle OPC, phi is equal to how much? It is half of 180 minus this angle, which is itself how much? Pi by 2 minus theta. Okay. So phi is equal to half of pi by 2 plus theta. Okay. So that is our phi. So how much is beta now? Beta is pi by 2 minus phi, because obviously this angle is 90. Okay. Just use this angle a little. So that is becoming how much? Sorry, pi by 2 minus 5. So it is pi by 2 minus pi by 4 plus theta by 4. Okay. So this will become pi by 4 minus theta by 2. So that is my beta. So this will have to be now plugged in over here. So work done, which is integration f dot ds from a to b, will become integration fr cos pi by 4 minus theta by 2 d theta. Okay, from theta equal to 0 to at that point theta I had taken as 30 degrees, so pi by 6 or whatever. So further you can write this as fr by root 2 cos theta by 2 plus sin theta by 2. Okay. This whole thing integrated from theta equal to 0 to theta equal to pi by 6. So this will be the work done. And now in case you're wondering how you will calculate cos theta by 2 or cos pi by 12 or sin pi by 12, how we'll calculate? We'll use this, that cos theta by 2 is equal to 1 plus cos theta square root. And sin theta by 2. Okay. Or let's do one thing, let's make it simpler by just taking this angle as pi by 3 so that we're not dealing with a tricky value. So pi by 3 can be. For now, you can do that pi by 6 one later. And the half angle is easy to calculate. So this work done will become fr by 2. Upper limit will become cos pi by 6. So that is root 3 by 2 plus sine pi by 6. So that's pi by 2. Minus lower limit will be cos 0, which is 1, plus sine 0, which is 0. Okay. So we will get this as fr by 2 into root 3 by 2 minus half, or 3 minus 1. 2 root 2, is it? Sorry. Yeah, correct. This is root 2, my mistake. So this will be, yeah, thanks for pointing that out. Yes, Nikita is correct now. Okay. So I will just change the value of theta in the original question. I mean this one. I'll change it to 60 degrees. Let's just change this to 60 degrees or pi by 3. Okay. So this was the proper integration method. But now I'll there are two trick methods of doing this, as I was telling you. Now I'll tell you the first trick method. Instead of taking this system, now we can take an equivalent system. Just take a minute, don't worry. Instead of this system, now we will imagine a system where something like this is happening. Okay, we have got a tiny pulley kind of thing here. Okay, and that small particle is tied by a thread which is going around that pulley. Okay. And that thread is being pulled with a constant magnitude force from this side. So we are applying a constant magnitude force F. So that is going to create a tension because it's a massless thread. So tension of, okay, that's the first thing. Okay. So now if you take the work done by F, that should be equal to the work done by tension on this. Okay. So instead of this, if you take your system, as the particle plus the thread plus the pulley, okay, then the work done by tension should be zero because it's internal to the system. So instead, work done by F is equal to change in kinetic energy plus change in potential energy of the system. Okay. So anyway, now work done by F is very easy to calculate because this point, let's say this point is Q. Okay. Now in the time when this goes from here to here, okay, this point moves from here to here. So whatever is the displacement of this point Q, okay, so work done by F is equal to what? It is directly equal to F into displacement of that point Q. Okay. So when you're going from this position to this position, okay, here this thread length was R root 2 and this thread length was some L, let's say. Okay. Now in your second position where this is 60 degrees, this has become like this. And this has become some L plus the displacement of the point P. And this has become some chord length, which is of 30 degrees. So let's say that chord length is Z. So Z plus L plus this should be equal to R root 2 plus L. So the displacement of this point is going to be how much? It is going to be R root 2 minus this chord length. Now how we'll calculate this chord length? We'll use trigonometry. So we'll have to use trigonometry where this angle is 30 degrees. So somewhere or the other you have to use that half angle formula actually. You can't avoid that. So this Z will become 2R sine 15 degrees. And sine 15 we calculate as square root of 1 plus cos 30 by 2. So you will calculate this Z like this, substitute it here, and from that you will calculate the work done as nothing but F into that displacement of the point. And you can show that that will give you the same thing as the method that we got earlier. So here you have to just calculate the displacement of this point P from thread length, how much the thread has moved forward without doing any integration and all that. So this is one of the tricks of solving this. There are two trick methods which I'll teach you. One is this. Next I'll teach in the following lecture next week. I'll take this up and explain it by a second method also. Okay. So we'll conclude here today, people. Some questions pending. I'll pick that up in the next lecture. But next lecture we will start with heat and thermodynamics also. Okay. So I'll pick up some of the pending doubts from work energy, and following that I will be moving on to heat and thermodynamics in the next lecture. In that we will start with the principle of thermometry and thermal expansion. Okay, so we'll be starting with heat and thermodynamics with linear expansion, surface expansion, and volume expansion, that coefficient of expansion term and all that, and thermometry, the principle of thermometry. Okay, so that's it for today's session, people. Wish you all the best.